Okay, let's begin. So before starting, let's look at what is it? Uh, okay, first go to the course website, reload this file. If there is any change or anything, it will be nice. Can you guys do it quickly? Yeah, once it is loaded, go to change runtime type and select GPU to make it faster and save button. Click on the save button, and one more thing, uh, clear all the outputs. Can someone say whether you reloaded and made the changes? Just drop yeah. So yeah, that's enough time for doing things, right? Okay, thank you. Now what are we looking at today? As you already seen, this is about constructing a convolutional neural network, and we do with C410 data set, and we do in two softwares like PyTorch, and we also use Keras at the end. So let's PyTorch and Keras. Okay, that's what we are going to do. All right, now yeah, that's there is a question about whether to use Keras or not. It should be fine. Like I'm it's like the point of covering these two is that whatever is comfort with you, and you go with that. Okay, if the question tells you that you can use Keras, yeah, you can use any of these softwares. Uh, you can go ahead and use. It doesn't matter whether it's Keras or PyTorch. Okay, and okay, I'm not going to debate about whether Keras is good or PyTorch is this, but it is about giving you an option of both. Depending on what you like, you can start building things on using that software. And Keras is very easy to implement, and whereas PyTorch is more class based, and you need to define classes every time, and it's slightly more difficult when it comes to, you need to specify many things when you're doing PyTorch. But PyTorch is more popular among researchers because of the same reason. It gives you more like control to you when you're doing these things. And so yeah, we look into both the options and you choose whatever you like. Okay, let's first uh, define some hyperparameters. The number of epochs, number of iterations we run 20 in this experiment, and number of classes we are restricting to, you know, C410 has 10 classes, and we take data corresponding to only 3 classes. The classes corresponding to 0, 1, and 2, we see exactly what are those classes, what are the names of those classes. And we used batch size of 100 when we are training the model. And the learning rate in optimization, we use Adam optimizer, and the learning rate, if you remember alpha, which is 0.001. Okay, just uh, with me execute this command just to start the simulation. Okay, and we need certain packages. You have seen all these things. There is a torch. Torch vision is data sets you can where you can get, and then it provides also there is utilities and to split the random split the data set and create a data loader, all these things. And the numpy, of course, we continue to. So execute this. This just gives header. Now this is where we are loading the C410 data set, and the data set is consists of training data set and test data set. And training data set consists of input and output. Output is label or targets, whatever you call. And the data output, this is represented in tensor. Uh, it's a tensor. What you get is a tensor. That's why we have this transform to tensor. Okay, once it loaded, just see what are the classes we have in this training data set. If you look at, there are 10 classes, number 0 to 9. First 0 corresponding to 0, you have airplane, and the next class, that is 1, is automobile, and the bird is class 2. So these three classes we use in our experiment. So, however we loaded, we'll separate that in a minute. And let's see what is the shape of the data we have. We have in the training data set, we have 50,000, and each one is RGB image. 3 represents red, blue, and green, 32 by 32 for each color. And then we have 10,000 for testing. Again, same format. All right. Now we are asking that, okay, we want, if you remember, in the here in a hyper parameters, we define 3 classes, 0, 1, 2, corresponding to airplane, automobile, and bird. And we are separating that data. We are ignoring other data corresponding to other classes. So now training data set has only data corresponding to 0, 1, and 2 classes. Similarly, test data. And now also we further split the training data set into trained data set and validation data set by using random split. Okay. If you notice, for when we are working with Keras, so we use train, test, split. Here, PyTorch has its inbuilt function to do this, and that's what this creates. So now look at the length of train data set and test data set. We have 12,000. Okay, and we can also include validation data set. So yeah. 3,000. Yeah, total 15,000 we have for 3 class, and validation plus training data set length is um, length is 15,000, and 3,000 for 1,000 for 3 classes in test data set. Okay, and now let's just print this some images. Okay, and we printed first 6 images from this data set. You can see that the bird is included in our data set. So first image, most of them are bird except one. This is airplane. if you increase number, you might see this automobile as well. Okay, now there is something apart from in Keras when we implemented, we are using NumPy array. Here there is a data structure called or class object called data loader. It will create a class object which contains more information, not just data set and labels. It contains more information and it's helpful in when you're working with PyTorch. So we create something called data loaders for each of them, training data, for validation data, as well as the test data. And this set of statements actually create that. Once we have, you can actually access the data and even its length just by executing the, yeah. And see, loader will have its data with name data set. Okay. And that data set has again 12,000 as you expected. And if you're checking for validation data set, 3,000, that's what we have given to the data loader, and 3,000. Yeah, that's what we expected. Now, just to again to demonstrate that we can access all the images from this train loader or data loaders, you can actually just look at a train loader and print the 15th image. Let's see what is that. And you see that the label is one. That means it's automobile. And obviously this is a car, so it comes under automobile. And okay, this is about loading the C410 data. Now, are there any questions so far? You're quite familiar with this already, so should be okay. Yeah. Now let's start creating a convolutional neural network. Okay. What do we have here? In this convolutional neural network, let me, I think Benoit actually created a shape in his assignment. Yeah, it's like, don't confuse. We have input layer, and that should be given to a convolutional layer, and with ReLU activation filter. And we want to do batch normalization after that layer. Then max pooling. Again, you have a convolution layer. You want to do batch normalization, max pooling, and after that, it's a regular uh, uh, deep neural network, where dense, which we built last time. So for that, we need to flatten the data. This layer actually flattens the data. And after that, it's just a deep neural network with 3 layers, okay, with the dropout after each layer. And finally, we have a softmax output layer with softmax. Okay, that's what we build now. Okay, let's look at it. So in PyTorch, there's something called a super class. That is essentially a class contains class. So you don't need to worry about it. It's a syntax you need to use when you're building uh, neural network in PyTorch. You can think of a whole neural network itself one uh, layer, and then you can build further on that. So this is the idea behind it, and the way it is developed using a superclass. And the module we need is NN. It's essentially neural network. So you load NN from PyTorch. Now let's define a class. In this superclass, what we have is that one convolutional neural network, convolution layer, that we call it C layer 1. It just it's a sequence defined by a convolution layer, and we need to add ReLU activation. Then we add batch normalization, then max pooling. This together actually creates one layer that is we calling C layer 1. And then we have a second such layer, call it C layer 2. This also contains first a convolution layer and then ReLU activation function. Then we do batch normalization and max pooling. After this, it's easy to understand. You have seen already. This is a fully connected layer where in Keras we use dense. Okay, when you're working with PyTorch, it becomes linear. And then we are again using ReLU activation function. And after this, in this we use dropout. We are not flattening data. We are not specifying any flattening thing here. It will be done in forward loop. We'll see. So that's what, like in Keras, we don't. I'm coming to these numbers in a minute. In Keras, we don't define any forward. It actually takes care of this. So that's why it's very user friendly, Keras, whereas PyTorch is, you need to specify more. If you look, we need to define all the numbers here. It doesn't really calculate on its own. Whereas in Keras, you see that we don't need to specify all these things. It will understand because it's sequences structure. Okay. So we start with the 32 by 32 into 3. So how many channels we have from input? Can someone type how many channels are there from the input data? 3, that's right. So each image is has 3 channels, and each channel consists of 32 by 32. So this number is essentially number of channels we are giving it to first convolution layer, and output channels is 8. This is in your hand, but I'm specifying here that, okay, let's take 8 output channels. Kernel size. So if you remember, we are moving in convolution, we are moving a kernel, and this, by giving 3, essentially you're saying it's a 3 by 3 kernel. Okay, when it's a symmetrical, like a square kernel, you don't need to mention this size. Suppose you want to give a kernel of this size, then you need to write like this. Otherwise, you can just specify that it's a 3 by 3 kernel, and you move that kernel, and then you need to define 2 parameters, stride and padding. Stride is 1, you jump 1 after the only one cell, and padding, you're familiar with these things. Padding, how many you add at the end around the frame. Again, padding can be 1 comma 0. It can be like this, but when it is symmetric, that is 1 1, you just need to mention 1. No need to mention 1 1. And so if you compute using padding and the formula given to us in this, that is input nx plus 2p minus nh by s plus 1. Uh, you guys remember that formula from Yoni's lecture? Yeah. So if you use that formula, you can compute that the output has 8 channels, and each channel creates an image of 32 by 32. Okay, you can compute. If I'm wrong, let me know. And then max pooling. it is nicely even number. So we don't need to worry. It just becomes 16 by 16 because we are taking a kernel 2 by 2 and making one cell. So it will become 16 by 16. Again, after max pooling, you don't reduce the number of channels. So it will continue to be 8. And now similarly, we do for convolutional layer 2, where the input is 16 times 16 times 8. And what that is number of channels, input channels are 8. And in this, for this layer, we are saying that, okay, let's have 4 output channels. And kernel size, I'm continuing to use 3. And stride is 1. Padding, I'm not doing any padding here. So this will reduce the size, as you can see from the formula. That's why we have 14 by 14 instead of 16 by 16 or more than that. So it reduces the size. Again, we just ReLU and batch normalization on 4 of them. That's why we need to mention 4 here. And max pooling, it's the same max pooling. So since it's a 14 by 14, we get 7 by 7 and channels won't change. After this, it's easy. It just, in the operation, we flatten it using this. Just I will get to that. Once data is flattened, what we get, it's a vector. Uh, we are combining all the channels and flattening all the data. That is 7 times 7 times 4. What do you get? That is what is the number here. So we are creating this is like a dense layer, consists of how much is 7 times 7 times 4? No? Yeah, so it will have 196 neurons and 80 outputs. Okay. Sorry, 196 inputs, so and 80 neurons, and those neurons give 80 outputs, and that is given to next layer. And we are saying that there are 40 neurons, and again 40 will be will like have 3 neurons at the end, which is output layer, and we are using softmax as activation function. Yeah, Rohan, that's correct. It's 80 neurons. And this is the input size of the data. Yeah. Now, unlike Keras, we need to define forward loop also. This is exactly forward propagation. What happens for a given model? Here it is referred as self. That's how we refer to like a model. When if you feed X to model, it will actually apply this layer, take it as input and output, and let's call it as output to layer 1, C layer 1, and that output is given to layer 2. That's how we know. And then the output of that layer will be flattened before we start feeding to fully connected layer, and so you continue to do it, and finally what you get is output of the output layer here. And that's how it's simple to define. Once you have defined this class, we need to class variable we can define, and that variable is essentially model. That is what we use to train. So this is the class, and you just apply, and you get model 1. Let's call it a model 1. And we also need to define what is the loss function we are going to use. This is cross entropy loss for model 1. And optimizer, as I said, we are going to use Adam in this lecture. And the learning rate is essentially uh, the one we defined already, 0.001. Okay. Yeah, so once you execute this, it should be ready with, let's run this class, and the class is ready. And now model one is ready. Just a small exercise. Okay. I'm keeping it here. Can you guys go ahead and take this code and address this task, modify this code for this class, and can you address this task one? Just go ahead. We got 2-3 minutes, and we are just making small changes in the uh, this class definition. When you're done, let me know. So this is the task. You must be having the task written on your. You need to calculate number, John. You need to calculate the number from the starting, just the way we did, and use the formula presented by Yoni. If you remember, there is n x. It is, Krishna, it is possible, and it is very model dependent. I mean, software dependent. So it's not consistent. How you add padding when it is a odd number, that will descend. Some softwares drop it out, the outer, like outer cells of the image, pixels of the image, to make it even number. Some actually add. So it's possible, but it's not consistent. And I don't think you will fall into that problem now. So if I remember, this is the formula. Okay, I think we can look at the solution. The solution should look like this. Instead of, we are using 5 by 5 here, kernel size. So if you calculate, you get 30 by 30 rather than 32 by 30, which was the case earlier. And so max pooling can be done easily. It will be 15 by 15. And for the next layer, we removed max pooling. So that's what is saying task is telling us. So we removed the max pooling. So we no need to worry about odd number here. All right. And after that, it's the same thing. Instead of 196, we get 676, and we flatten this before giving. That is done in the forward loop. And after that, it's the same thing. We have 80 neurons in the first fully connected layer and 40 in the second fully connected layer. And finally, output layer. It has 3, obviously, and softmax. You guys got it? So we calling a model 2. And once practically is done, you can play around with this, and we don't really use it further anymore. Anyone has any difficulty in building this?
Sorry, Sarat. So my question was, when I said with the output size of the FC1, it's 80, that's the same as before. Does it really matter what that number is?
Sorry, which one? You're asking about the question. You're not sure what output size should be of FC1, right?
Yeah. So is 80 right?
That's just a choice we are making.
Okay.
This choice, and yeah, you can do it just like other dense layers where we have this freedom as an hyperparameter. Yeah, this is just an hyperparameter. We are fixing it for the demonstration.
Okay, thank you.
Yeah, cool. And yeah, in the same way how we define model 1, we can define model 2, and then we have a cross entropy loss and everything, blah blah blah. Okay, now let's train the model 1, which we built already. Okay, this I don't think we need to run, but yeah. Okay, to train, while training we calculate performance also. If you remember, we use validation, we compute a validation accuracy and validation loss, as well as the training loss and training accuracy. So we define a function here that can do all these tasks, because we don't want to rewrite it again and again. What it does is that it takes the model pointer, the class value, and we have a loader. Loader is essentially, if you're asking evaluate for validation set, then we have validation data loader. That's a second input. And what is the loss criterion we are using? If we input these 3, it should output loss for that data, loss and accuracy. Okay. If you look at it, it's easy to understand. Suppose, look at this, sorry, look at this model 1 loss criterion. Okay, this is this actually returns a function. There's like a pointer to function. So if you actually input, loader consists of data in batches. If you take a validation data loader, it consists data in batches. Each batch consists of 100 in this experiment. So when you actually take images and labels, it is actually batch image. So it goes through batches, and images actually goes through each batch and the corresponding labels. And for each batch, we are computing what is the output when you input it to the model. that exactly runs this forward loop and computes the output. And loss criterion, if you put outputs and the true labels, you know what is the loss. Essentially, it computes the number of mismatches and gives you that loss. What is the fraction of things are not matching. Once you get that loss, it is a torch. It's a tensor. So we need to take out the item. We are just maintaining a list to get the losses for each batch. So this loss list consists loss values for each batch, and we are actually number of images used, that is captured by total, the parameter total, which just adds length of each batch, and how many correct predictions happened, that gives the accuracy. So when you look at the written statement, we added over all the batches for entire data given to us. We added all the accuracies and multiply it to 100 just to make it a percentage. And also we have a loss here. This is a it evaluates loss and accuracy. It is easy to follow. And then we want to define a training a function to train the model. So we call it a train model. It takes model and the corresponding training data loader, validation data loader, loss criterion we are using, and optimizer we are using for the model. And again, it goes through number of epochs. We said the number of epochs are 20. So it actually like goes through all the epochs, and each epoch we go through entire data. And again, just like earlier, we get each batch in the data. We separate the images and labels, and again compute loss just like earlier. And the key point is here where we execute backward propagation. Forward propagation is easy. We have seen just put images into model and it give you forward propagation. For backward propagation, you need to do these three things. It just first gradients, initializing gradients to 0, and then this is exactly where you get backward propagation. I would recommend you to just go and read the documentation about this particular backward propagation command in PyTorch. And there is a question: is images a part of the loader class? I thought it should be data set. So loader consists of data set. Loader is a big class which actually knows how the data is split into batches and other things. Okay. It contains labels as well as data, input data. Uh, do you understand, Christina?
I kind of get it. I'm just wondering what the indexing's doing. Just because I don't understand where images has come from.
So this enumerate actually takes the data from this train loader, which has data as well as the details about how we are creating batches using that data. And it actually looks at the number of batches involved and enumerates those batches. So I carries index of batch, first batch, second batch, third batch, like that. And each batch you get images and labels separately. So in this images, you get 100 images each time and 100 labels you get.
So that's just saving the images and labels to images and labels. It's not actually calling images from the train loader.
Yeah, but this is a variable which actually contains first batch of images, and then in the second iteration when I is equal to 1, it contains the images of second batch.
Okay, the indexes of the second batches.
Yeah,
Okay.
yeah. So I changes along with these batches, and yeah,
Okay. Yeah.
yeah. For each batch we do this, and you do forward propagation that is computed like this, and backward propagation done here, and we see optimization step here. That's it. And these are other things are just calculating, tracking the accuracy and loss. This is how many labels are predicted correctly. And also we want validation accuracy and loss accuracy. So after each epoch, we input validation data or validation data loader to the evaluate function here, and compute what is the loss and accuracy. That's what given to us. And we store them in a list for later plotting things or analyzing things. And let's go ahead and execute these two cells. Yeah. Are there any questions on these two functions? No? Seems like everyone got it. All right. So finally, we need to actually train the model. We have a function which can train the model, and also a function which can evaluate accuracy and loss. So all we left with is just use this model one, and the optimizers and loss criterion we already defined, and input that to train the model, and we get train loss. This is a vector of or list of train loss, okay, for all the epochs. And similarly, training accuracy, validation loss, validation. So can someone tell me like how many elements in this train loss once we apply this? How many elements we expect here in train loss? That's correct. We have 20 epochs. So each of this one is a list consists of 20 elements. Let's execute it. Go ahead and run this cell. Yeah, it takes a while. You can see how it is progressing. Maybe not a bad idea to actually move quickly. Let it run. And this is just, you have seen in the previous practical how to plot training loss and these things. So I won't be explaining so much. It just takes these vectors and plots them. We are almost done. Yeah, not bad, I guess. Started with 66 and 91. That's good. It's done. And finally, we have this accuracy. Anyway, let's plot this by running this. So this is how it looks. Training and validation accuracy and the loss going down like this, right? Good. Looks nice. Are there any questions so far? No? Okay. So far we have trained the model, which is we calling model one, and we plotted the corresponding training loss and validation loss we obtained during training. And you know why we need I am using fixed number of iterations, but you can always use validation loss or accuracy to terminate the thing as like early stopping we studied earlier. You can implement all those things. I'm not going to talk about them here, but you just need to include that in this train model. and say that once you have validation loss and training validation accuracy, you can actually use that as a criterion to stop early if things are not changing or loss is actually increasing. Suppose some point it is start increasing. If it consecutively for 5 times it increasing, you can stop it there and say that, okay, I will take value where it is minimum. Okay, but ultimately we want to test it on the test data set, and that can be done as follows. We have defined already evaluate, and that can take model and the data. Here the data comes from test data loader, and the criterion is cross entropy. So we need to feed that as well. Once we have since we have this function already, we can just go ahead and execute it, and it will output here accuracy list and test loss. And you see that there is 83.16 approximately and accuracy, and 0.71 is the loss. Not so bad. Maybe when you have time, just go ahead and tune things around. And one of this is task 2. I didn't see much improvement by this the model we have in here, which is asking to add more 2 more convolution layers, right? And remaining is essentially same 3 dense layers, and total we have 4 convolution layer. This is just a practice, and we do not have much time, so I would request you to go through this and see yourself whether you can achieve some improvement or not by adding this, and just run it as we go. And you might like you can report your accuracy and loss on test data once it is done executing. Okay, for model 3, while we start looking at Keras, you keep running this. And is that clear? Just execute these cells also. It will be running, and just report what you see as test accuracy and test loss eventually. Okay, let's look into Keras. Again, in Keras, is everything is in NumPy array format. So just like MNIST data set we have seen earlier, we can load data set C410 data set from Keras. Just keras.datasets have it, and you can load it as a training X, training Y, test X, and test Y. And we have to wait until this cell is executed. It's almost done, I guess. It's taking time. Yeah. Anyway, this gives us training X and training data and test data. This is just use this. We are printing number of classes here, and we are also printing an image. But the data is not normalized, so we need to normalize it to make it each value between 0 and 1. So this cell essentially normalizes as we have seen earlier. Okay, we were done with the simulations. Okay, good. And can someone report what you have achieved as a test accuracy and test loss for model 3? I got 82 point, around 82.82. No one else executed this. Okay, 84, that's a good number. 81. Okay, that's all right. You can just enter when you have the output. I will take another 82.9. That's nice. I'll take another 5 minutes to complete this practical. Okay. All right. So just like last practical, we actually loaded the data here, and we need to separate first three classes, 0, 1, and 2. That's what we do here. And we calling it a small train X, small train Y. And let's print one image of this train X. What are the values we have? Yeah, this is already normalized. So good. Okay, we have small train X and small train Y, and this is just data corresponding to three classes. And look at what is the size. As you know, it's supposed to be 15,000. So we have 15,000 images, input images, and labels 15,000. And similarly, we do it for test data. We separate 84. That's very good accuracy, I guess. Thank you. And now, as you can guess, the test after removing three classes, because each one has 1,000. So again, we have 3,000 here for test X images, and the labels also 3,000. Now we need to split this into training data and validation. Just like earlier, we use sklearn model selection, and we use this particular package called train test split. And once we have, you can see that the training data set we are going to play with has 12,000 images, and the validation set has 3,000 images, and tests. So the 12,000 labels in the training set and 3,000 in the validation set. One thing which we didn't do in PyTorch is converting to one heart. It is not required. You can do it and modify it to represent one heart, but PyTorch it can handle without changing into one heart. But in Keras, we need to make it to one heart, where if you look at each array has 3 elements. For if this is corresponding to an image which is a bird, that's why you get one here, which is representing this image corresponding to bird, first image corresponding to bird. And if you have one here instead of here, then it is what is it, automobile. If it is one here, then it is a airplane. Okay, so now we are ready to construct the same neural network, convolutional neural network. And if you remember, we have two convolutional layers in earlier example, model 1. So we repeat same thing. We call it a model Keras, and we have sequential definition here. And we add layers one after the other. And first one is convolution 2D. We no need to specify how many inputs are we giving, but we need to specify how many channels are required, and that is 8. Kernel size is 3 by 3, just like that. Strides here we need to mention like a list 1 by 1. And padding, you don't have padding 1 0, but instead it's called same or valid. Just look for the documentation on that. Valid is essentially equal to padding being 0, where same is given when you don't want the dimension to be changed. Like suppose you are giving it 32 by 32 and you want 32 by 32 as output image, then you put same, and padding will be adjusted so that it will be the same size. That's why Keras becomes so user friendly in that sense. And activation again ReLU, and we need to mention what is the input shape. And so once it is created, we again using batch normalization. Max pooling is defined very similar way. Here we use add every time we make add a layer. You can think of each one is a layer. Similarly, we define next convolution layer, which batch normalization and max pooling. Here, unlike in PyTorch, we need to define a layer called flatten. It essentially flattens the whole matrix and creates a vector, flattening all the channels and all the matrices, and creates a vector that is given to a dense layer with 80 neurons. And then we use dropout, just like earlier. Uh, Again, another dense layer with 40 and dropout after that. And this is the final output layer, right? It's just very, we just did exactly what we have done. And you're familiar with Keras that we need to compile and then train it. So this is easy. I just copy pasted functions from the previous practical, and let's execute. Yeah, this, let's execute this definition of model. It's taking some time. Yeah, it's done. And then execute these functions as well. Okay, we have function that can compile, and we have function that can train the Keras model. And now do both of them. So if you notice, this is a summary of the network, and yeah, we got exactly the same numbers if you look. So Keras can actually determine what is the size, which is not done in PyTorch. So you need to be careful. And so yeah, this is where we get to see the output. Yeah, we are done. And if you look at what is the accuracy, training accuracy is 85% approximately, and validation accuracy is 84%. And losses is better than PyTorch version, I believe, speed and other thing. But I have read several places that Keras is user friendly, but it will have a difficulty in executing um, like huge data. So people use Keras mostly to learn and develop uh, models which can handle, which doesn't handle bigger, larger data. But when you're really playing with huge data, people suggest to go for PyTorch. Maybe I'm wrong. That's what I heard or read about these two models. Okay, let's see test. We got test evaluation. Unlike in PyTorch, we already have a defined function in Keras, so we just use it. Once we had test evaluation, that is uh, essentially computing accuracy and loss on test data. We can print that. So this is how it looks, and we have test accuracy 83%, test loss 0.4. That is about today's practical. I would be happy to discuss if you have any questions. Thanks for listening to me. No questions? Thank you, guys. Okay, then, if no one has questions, see you guys.